Hello, my name is Nikhil Naik and today I'll be presenting my data visualization project on aviation safety. Firstly, let's explore what this project was about. A common misconception within the world of aviation is the information portrayed about air travel safety. This includes the generalizations of statistics portrayed to the general public with the chance of being involved in a plane crash. This information doesn't factor relevant influences on aircraft accidents and incidents occurring, including geographical location, average fleet age, as well as a safety improving industry. The project will be looking into multiple factors that affect aviation safety from accidents or incidents, including geographical location, time period, aircraft age. The goal of this visualization project is to provide us as travellers a more accurate and alternate perspective of aviation safety when travelling around the world. For analysis, the term accidents will refer to fatalities and incidents refers to non-fatal aviation crashes. Now let's move on to why I undertook this investigation. The reason for undertaking this project was because from research conducted, not many travel advisory resources show any direct comparisons between aviation accidents or incidents with geographical location. Furthermore, no analysis of existing aviation data has been analysed and compared in the process of location, fatalities and current time period. With the IATA predicting the number of people travelling in aviation set to increase by 8.2 billion by 2037, this analysis will provide us as travellers a resource to make a more informed decision when travelling around the world. For data collection, multi-dimensional datasets were sourced from 3 different providers. The first dataset showed the accidents or incidents from 2006 to 2018 and was sourced from the ICAO. The file downloaded was a CSV file given by using a key to access the API. This data source was most useful since it contained both accidents and incidents, as well as aircraft type, country, fatalities, years, which coincides with the aims of this project. The dataset also contained geographical coordinates of the nearest major city to allow plotting of a visualization of the distribution of airline accidents and incidents. The next dataset contained fields for the number of passenger movements per country from 1987 to 2018. This was retrieved from the World Bank Organization as a CSV file with all countries in the world that have both domestic and international travellers. This would be used to create a visualization for the chance of being involved in an airline accident or incident from a geographical location standpoint. The final dataset that was used to understand the age of aircraft operating within a country and how this influenced aircraft accidents or incidents. The dataset for this information was gathered from Kaggle statistics and downloaded as a zipped CSV file containing airline operators and their aircraft's average fleet age. For the ease of access to datasets with the CSV files, they were all stored within folders correlating to a type of graphical visualization. This ensured filtration of one file didn't impact on another visualization using the same dataset. Many null fields existed which didn't correspond with MATLAB's format. Since these fields represented 0 fatalities, MATLAB would recognize these as not a number. Hence, I ran an Excel macro script to replace all these fields to 0. Next, for the purpose of constancy of time, all datasets were passed to only be from 2008 to 2018. This allowed multiple datasets to be combined and correlations to be made within the same time frame. This pre-processing was done in Excel with a macro script ran to omit all fields that lay outside this range. Also, for better comparison, a macro script was run to omit countries with less than 10 accidents or incidents, which reduced the datasets from 20,000 to 2,000 entries. An issue that was later discovered was that the United States included accidents and incidents from private and charter aircraft. This diverged from the scope of the project, hence the United States had to be omitted from some visualizations. The execution of transforming the datasets into visualizations was done mostly through MATLAB and some visuals created using the online software Plot.ly, Boxplot.r, and Visual Paradigm. MATLAB was used as it was a free accessible software and I had past experience in using it. The websites Plot.ly, Boxplot.r, and Visual Paradigm were also used for visualizations where MATLAB lacked the ability to create such different multi-dimensional figures. For an overview of the aviation accidents and incidents that occurred between 2008 and 2018, MATLAB's GeoBubble plot was used. This multivariate function took the latitude and longitude approximations of the incidents or accidents and fatalities and placed them on a global map. With the scale of the bubble varying, this makes it easier to visualize the geographical distribution of fatalities. Smaller bubbles indicated non-fatal accidents and larger bubbles indicated a fatal accident. The color terrain as a base map property supports our understanding of the type of environment the incident or accident occurred in. From the plot, it is evident that the United States has a higher cluster of accidents and incidents due to the higher frequency of plotted bubbles on the map. However, the size of these bubbles are mostly small, suggesting a high frequency of non-fatal incidents. Regions of high fatalities include Western Europe, Central and Southeast Asia, which is illustrated by the larger relative bubble size. This geographical plot was an effective way to illustrate multidimensional data, enabling the visualizations of incidents and accidents around the globe. The first scatterplot visualization shows the number of accidents and incidents per year from 1990 to 2019. Using MATLAB's linear regression function, a linear plot and higher order polynomial nonlinear fits of increasing degrees was plotted for extrapolation. Using this regression model, I applied interpolation to deduce a reduction in aviation accidents and incidents within the next 10 years. However, this model most likely should not be extended beyond 2030 due to a changing industry, more aircraft, regulation changes, newer aircraft, and changing pilot training. It is evident that there is a decline in accidents, hence a historical projection of an improvement in aviation safety. When analysing the validity of the regression model, the residuals plots was vital to measure the accuracy of this regression model. The linear model shows an oscillation motion, which is not the random pattern to indicate a good fit for a linear regression model. By using a subplot of the residuals for a linear and nonlinear fit, we can see an improvement with the residuals with the third degree polynomial fit curve fitting the residuals, which are smaller and systematic positive and negative variations is minimum compared to the other fits, somewhat coinciding with the U-shape required for a good fit. Using this, I was able to validate the precision and accuracy using a third degree regression for my visualization. MATLAB's 3D scatter plot was used to visualize the relationship between aircraft type, fatalities, magnitude, and the year within a country. The standard MATLAB output was hard to read with black crosses appearing on a grey background. Hence, the principles of light on dark was applied to place lighter data points on a dark background. For interpreting the three-dimensional position of data points, the grid was turned on and bolded, which made it easier to visualize the position of data points on this multivariate plot. From these plots, we can visualize almost exactly where a specific accident took place and the number of fatalities and aircraft type involved within a country. From this visualization, it is evident that Russia has a spread of fatal and non-fatal accidents within the decade. There exist two clusters of non-fatal incidents at the start of the decade and a cluster of fatal accidents at the end of the decade. Russia has a spread of modern 737s and old A320 aircraft involved in non-fatal accidents. However, it can be noted that the fatal accidents involve both old Tupolev and Yak aircraft designs in the 1960s. More concerning is the two fatal accidents involving their newest aircraft, the Sukhoi Superjet, which was designed in 2011. This analysis of high-frequency incidents and accidents occurring both in older and newer aircraft suggests an issue with the safety of Russian aviation with both older and newer aircraft. From this US plot, there seems to be a high frequency of incidents throughout the decade. The important understanding is the majority of incidents are non-fatal. From this, we can see the US has a large number of incidents that are non-fatal, that the smaller private or charter aircraft hold the majority of fatal accidents in the US. This visualization analysis lets us understand that the US has a majority of non-fatal accidents with large commercial aircraft and less than 6 fatalities in small or private charter aircraft. The online graphing tool BlocksplotR was used to create a box and whisker plot by uploading a CSV file. To add features to the plot, the selectable property tool was used to add a mean, whisker, maximum, and median. This allowed for visualization analysis and interpretation of the distribution of fatalities and accidents. A consideration that had to be made when comparing the boxes was the issue of colorblind people. To accommodate colorblind people being able to interpret the visualization with the color pairings, green, red, brown, and orange were mitigated. From the box plot, it is evident that most countries, the maximum whisker is separate from the third quartile, suggesting at least one major accident with high fatalities. Looking at the visualization, Iran, Russia, and Pakistan are skewed left, meaning the majority of accidents that occur in Iran, Pakistan, and Russia result in a high amount of fatalities. The other countries are skewed mostly right, meaning a low amount of fatalities and the majority of fatal accidents. This skewness can be interpreted as more than 50% of accidents occurring in Pakistan and Iran result in more than 60 and 80 fatalities. I investigated how possibly aircraft age and poor maintenance with certain countries have an impact and involvement in accidents and incidents. The most appropriate tool to visualize this was the rose chart. The MATLAB function to create a rose chart was more orientated to directional magnitude, where aircraft age wasn't directional. Hence, the online graphing tool visualization paradigm was utilized to construct the visualization using an imported CSV file. The stacked feature was also applied to easily distinguish the age of multiple aircraft used by a single airline. Countries of concern include Indonesia and Pakistan. From this visualization, the operators Indonesian Lion Air and Garuda Indonesia and Pakistan's PIA operate older aircraft of ages above 25 years. These aircraft are of particular concern being built in 1989 and 1994, require a high level of maintenance than newer aircraft. From analysis of the geographical bubble plot previously, we can interpret flying on 747s and A310s into Indonesia and Pakistan poses a higher risk of being in an accident or incident. The Heatmap enables the visualization for analysis of the progression of individual countries of their accident distribution. From the plot, we can deduce individual countries' projection and performance within a 10-year period to understand how they might perform in the future. To create a figure, the dataset used was filtered for only fatal accidents at a maximum of 12 annually. This was done to ensure a fair and honest comparison between countries around the world. To create this, the online tool Plot.ly was used to create this heatmap plot. The online software simply took a CSV file input and a simple interface to customize the plot. From this heatmap figure as a whole, we can visualize different countries' progression of accidents and the decrease in frequency of aviation accidents as a whole, with a low amount of pink near the end of a 10-year period. This reduction supports the earlier interpolation of best fit, such as the industry is having less accidents and becoming safer as time progresses. MATLAB's vertical bar graph plot was used to visualize the chance of being in an aircraft accident or incident based on location, passenger movement, and a country's aviation safety history. To create this model, two separate CSV file datasets were used, which had to be filtered to only include data from 2008 to 2018. With this vertical bar graph, we can comparatively visualize the chance of being in an aviation accident for different countries with a chance in a million. It is interesting that Russia, with more accidents, has a less chance of being in an accident than Australia. We can explain this with the large number of passenger movements in Russia than Australia, correlating to the smaller chance. We can read this graph by seeing how far the graph extends along the x-axis. For example, Sudan has a 2 in a million chance of being involved in an accident or incident, whilst Australia has a less than 0.001 chance of being involved in an accident or incident. In conclusion, from all the visualizations developed, it can be deduced that countries with potential problematic aviation safety include Russia, Pakistan, Iran, Sudan, Nepal, Myanmar, Afghanistan, Bolivia, Canada, and Indonesia. Thank you for listening.